Welcome to the WeEn Semiconductors contribution to Bodo's Wide Bandgap event 2020. My name is Huijink and I'm the Technical Marketing Manager in WeEn Semiconductors. In this presentation, we take a closer look to practical aspects of designing in silicon carbide components in automotive applications. Here is the overview of the presentation of today. We will be looking at automotive charging applications, EV charger, that's the stationary equipment, and the onboard charger, OBC, that's located in the car. We will be looking at application design aspects of silicon carbide semiconductors, but also we look at passive components and some non-wide bandgap semiconductors like SCRs and triacs. We also look at silicon carbide semiconductor test and measurement for different parameters, static parameters, dynamic parameters, and rating parameters. First, we look at automotive charging applications. On this slide, we see a simplified schematic overview of a stationary EV charger. It is a three-phase application, and we see a Vienna rectifier stage that actually combines the input rectification with power factor correction. In the middle, we see the connection to the mains neutral. So this Vienna rectifier stage delivers both positive and negative DC voltage. And this feeds into a full bridge dual LLC stage. These silicon carbide MOSFETs are controlled, and the frequency of control actually determines the output power into the load. On the secondary side of the transformers, we see a high frequency rectifier stage that's done with 4 silicon carbide diodes. The plus and minus terminals are connected, and then we charge the battery that typically has a voltage of 400 volt or higher. On this slide, we see a schematic diagram of the onboard charger, also called OBC. This is a single-phase application. We see a bridgeless rectifier stage. This combines the rectifier bridge and the PFC. This stage delivers high voltage DC to a full bridge LLC stage with 4 silicon carbide MOSFETs. The frequency of control again determines the power delivered to the battery. On the other side of the transformer, that also delivers galvanic isolation, we see the high-frequency rectifier stage consisting of 4 silicon carbide diodes. And then there is the battery that is charged. Now we see the simplified schematic diagram of an onboard charger that can also be used as an inverter. The diodes have been replaced by MOSFETs. With this application, we can deliver AC power to the mains and to the home. If we start at the right, the full battery powers an LLC stage with a full bridge MOSFET. Then we have the galvanic isolation with the transformer. Then we see the high frequency rectifier stage, high voltage DC, and then the inverter stage that converts the high voltage DC to AC. If we take a good look in the diagram, we see that the bridgeless rectifier stage for normal operation has become the inverter stage for inverter operation. And the LLC stage of normal operation is now the high frequency rectifier stage. And the high frequency rectifier stage in the normal operation has become the LLC stage. Now we have a look at application design aspects. Let's have a look at tendencies in EV charger applications. For the EV charger, it is important to have a high power so you can quickly charge the vehicle. Over time, they should become cheaper, smaller, and run at high efficiency. EMI is always important. The application should generate as little EMI as possible. And of course, we need to apply PFC because this is a high power application and the utility companies will require PFC. For the onboard charger, weight is important because the onboard charger is in the car. It should be light, small, and also do a high efficiency power conversion. As an option, there can be bidirectional operation. So in this case, the onboard charger is not only a charger for the battery in the car, but also an inverter, so we can actually deliver power to the house. Also here, low EMI is important. Now let's have a look at the semiconductors, the silicon carbide, diodes and MOSFETs. Important for the silicon carbide Schottky diode is a high blocking voltage, a low forward voltage drop, and a very high switching speed. The material silicon carbide inherently is always very good for high blocking voltage and very high switching speed. On the right, we see a graph of forward current as a function of voltage drop for one of the latest 1200 volt WeEn Semiconductors silicon carbide diodes. For the silicon carbide MOSFET, also high blocking voltage and very high switching speed are very important. And of course, a low on-state resistance. In the picture on the right, we see, for instance, substrate resistance and channel resistance. Let's have a look at our silicon carbide Schottky diodes with MPS structure. When you switch on a utility mains connected application, this often leads to a high inrush current. The semiconductor components, mostly the rectification and PFC diodes, must be capable to deal with the so-called high IFSM. Pure Schottky diodes are generally not the best option when high IFSM rating is required. A Schottky bipolar hybrid, the so-called merged pin Schottky, overcomes this shortcoming of the pure Schottky diode. Let's have a look at the side view of the die of a Sic Schottky diode with MPS structure. We see with the yellow arrows the nominal current. On the sides we see special P+ implantations that take care of the surge current. These are actually PN diodes in the Schottky diode. Let's have a look at the graph bottom right. These are the forward characteristics of two diodes at 25 degrees Celsius. Vertically, we see forward current, horizontally the VF voltage drop. The red line is an MPS diode. The dotted black line is a JBS diode. In this graph, we clearly see that the bipolar mode kicks in when the current density in the die gets very high. This means the MPS part has a better inrush current capability. Now let's have a look at the passive components and some non-wide bandgap semiconductors that can also be used in EV chargers and onboard chargers. First, we have a look at the passive components. The higher the operating frequency of an application, the lower the value of the inductors and the capacitors. If you have a lower value inductor, it is smaller, cheaper, and lighter. And also, if you have a lower value capacitor, it is smaller, cheaper, and lighter. Non-wide bandgap semiconductors can be used to limit the inrush current. For instance, SCRs, silicon-controlled rectifiers, can be used in a controllable rectifier bridge. In the picture at the bottom of this slide, you can see that in a rectifier bridge, two diodes have been replaced by two SCRs. And here we see a similar solution using a triac. The triac is switched at voltage zero crossing, and in this way we limit inrush current. Now we have a look at the test strategy philosophy. There are various ways that guarantee that only good products are delivered to our customers. Firstly, we have the full production test. A number of parameters are tested in production on high-speed automated test equipment, also called ATE. And we do laboratory tests, sample tests. Parameters are tested on a sample basis. The outcome of the test is representative for the whole production batch. And we have guaranteed by design. Here, parameters are not measured per device or per batch, but during the product design, these parameters are controlled and measured in an R&D environment, and relationships with other parameters that are measured in full production or during batch sample tests are confirmed. A pass on the measured parameters also implies a pass on the parameters that are guaranteed by design. For parameter tests, we distinguish static, dynamic, and rating parameter tests. Static parameter tests for silicon carbide Schottky diodes are forward voltage drop. This is done at several forward current levels, and this is a full production test. Another static parameter is reverse current. Also, this is done at several reverse voltage levels, a full production test as well. And breakdown voltage. This is done at several leakage current levels, a full production test. The thermal resistance at a typical condition is guaranteed by design. For silicon carbide MOSFETs, RDS on at several drain currents and VGS levels is a full production test. Reverse current at several reverse voltage levels is also a full production test. And VDS at several reverse current levels is a full production test. Again here, the thermal resistance at typical condition is guaranteed by design. For dynamic parameter tests, for silicon carbide Schottky diodes, we test QR, reverse recovery charge, and CD, junction capacitance. In the picture bottom left, the red line shows the extremely low QR for silicon carbide Schottky diodes. For silicon carbide MOSFETs, we measure QGD, QR, different capacitances like CISS, COSS, and CRSS, TR, TF, TD on and TD off, and E on and E off. Rating parameter tests are done for both silicon carbide Schottky diodes and silicon carbide MOSFETs. For the diodes, for example, we do the IFSM, inrush current, IFRM, I2T, fusing, and ERSM. And for silicon carbide MOSFETs, for example, we do IDM, ISM, EDS, and safe operating area. Testing rating parameters is an interesting job, because if you really want to know what the IFSM of a diode is, you have to test it to destruction. That would be like testing matches in a matches factory. Unfortunately, you could not sell any matches anymore. So we test these rating parameters up to a certain level that we want to guarantee. In summary, we can say that silicon carbide power semiconductors are becoming mainstream throughout the industry for EV chargers and onboard chargers. EV chargers and onboard chargers can become smaller, more economical, and more efficient by switching at a higher frequency. WeEn silicon carbide diodes and silicon carbide MOSFETs help to enable these high switching frequencies. If you have any questions, please drop me an email. The email address you can find at the bottom of this slide. Thank you very much for watching the WeEn Semiconductors contribution to Bodo's wide bandgap event.